Okay, I is everything fine with the presentation?
Yes.
Okay, so yep, let me get started. So the title of my talk is Magnetic Phase Recognition of Artificial Kagome Spinice through Initial Magnetization Curve. So, for almost 20 years, arrays of nanomagnets have been attracting the interest of the community of frustrated magnetism and statistical physics because they can act as artificial spin systems. And to understand that, consider a nanomagnet that is small enough to be a monodomain and elongated in such a way that its magnetization point along its length. So this object has only two stable configurations, let's say up state or down state. So effectively, this behaves as a mesoscopic version of an Ising spin. And you can use it as the building block to construct an array of these nanomagnets. And in this image, I'm showing here some of the various lattices that have already been reported in literature. And such systems can be easily fabricated with lithography techniques, and this gives you a direct control over the lattice geometry and the interactions between these nanomagnets. And in turn, you can experimentally realize several spin lattice models or mimic real materials. So in the beginning, they were used to mimic spinized materials. So that's why these arrays are also generally referred as artificial spinize, although nowadays they go beyond that purpose. Um, anyway, since then, a lot of magnetic phases have been reported, including ferromagnetic and ferromagnetic ordering, more exotic orderings, correlated disordered states, and the list is really long. But what you can really realize is that the experiments on this research field heavily rely on magnetic imaging techniques. So that's why under the image of the slide here, of this slide, I put the name of the techniques that were used to produce them. And that's for a good reason, because such imaging techniques allows you to have a direct visualization of the spin configuration, something you can't usually have with real bulk materials. So on the one hand, this is very powerful, and that's one of the reasons why this area have thrived so much. But on the other hand, there are some practical drawbacks. These techniques, they are time consuming. So to have a good high quality contrast image, it usually takes days or hours in best case scenarios. And they are not always accessible. For example, XMCD pin requires synchrotron light source. So we started thinking about some way to circumvent these issues, and we wondered if we could determine the magnetic phase of artificial spinices through the initial magnetization curve. In principle, this can be measured by a simple magnetometer, which is an equipment that can be found in laboratories worldwide. And the measurement itself would, in principle, again, it can take minutes or seconds. So to validate this idea, we chose a specific system to be our study case. And this system was artificial kagome spinice. So in this system, we have the nanomagnets arranged on top of a kagome lattice, and they interacted with one another via dipolar interactions. And we picked this system because this model is known to have a very rich phase diagram with four magnetic phases. A, a high temperature paramagnet with completely disordered states, uh, the so-called spin-ice one phase, where it is still disordered, but it has short range order, where each vertex here obey the so-called ice rules. There is a spin-ice 2, where in addition to the ice rules, the vertex charges order, and so they crystallize, but the spins can still fluctuate. And at very low temperature, the system reaches its six-fold degenerate ground state with long-range order both of spins and charges. Uh, all right, so the first thing we did in this work was to perform Monte Carlo simulations of this model on a 12 by 12 kagome lattice. And with it, we randomly selected 100 distinct microstates of each phase. Now, as I said, the long range order phase is only six-fold degenerate. So to get 100 microstates out of it, we actually did a trick. The microstates of this set actually have 85, like a large portion of respecting long-range order pattern, but there is a small remaining part obeying only spin-ice 2 constraints. So for the sake of clarity, I'll be referring to this set here as quasi long-range order, and it will be clear in a moment why I need 100 microstates and not only 6. Well, anyway, uh, we used these 400 microstates as the initial states in micromagnetic simulations of an equivalent 12 by 12 kagome lattice of nanomagnets. So we mapped the spins orientations to the orientations of an uniform magnetization for each nanomagnet. So this picture here is showing an example of an initial states of spin ice 1. And then we applied a magnetic field in this direction until the sample gets saturated in the simulation. And from it, we extracted its initial magnetization curve. So here are the results. Each curve here is the average over the 100 curves for each phase. And what we can immediately see is that the paramagnetic and spin-ice 1 curves, they are clearly distinguishable, even considering the error margin here. However, spin-ice 2 and quasi-long-range order curves show considerable overlap, so we cannot distinguish them only by visual inspection. So to do a better work, we define 6 parameters to characterize these curves in more detail. And here, for example, is just an example of the curves. And let's say the initial magnetic susceptibility, for example, is considered as the slope of the curve in this initial part where it has a linear trend. And really, each of these parameters has its own definition. I won't go into the technical details here, but what really matters is that we can straightforward calculate these parameters for each curve, and that's what we did. We calculate the value of them for each of our curves. And here I'm showing the distribution of the 6 parameters for each phase. So in a general manner, we can see that the paramagnetic and spin-ice 1 distributions, they are well separated from one another, what makes sense. Whereas the spin-ice 2 and quasi-long-range order distribution, they again show an overlap, but we can see that quasi-long-range order, it tends to be sharper. And so there are some slight differences between spin-ice 2 and quasi-long-range order. For those who are familiar, we can also see this distribution through the principal component analysis. So we see a paramagnetic set separated from the spin-ice 1 set, and spin-ice 2 and quasi-long range order overlapping. And our final task was to use a supervised classification algorithm to predict the phase of the initial microstate given only only the curve parameters. So to do that, we used a support vector machine. 70% of our data set were used as a training to classify the remaining 30%. And this is our result. So the algorithm correctly predicted the phases of all the paramagnetic and spin ice 1 curves, which was expected. I mean, I could do it. But what was impressive is that it correctly predicted 75% of the spin ice 2 curves and 89% of the quasi-long range order curves, which is astonishing because due to the apparent equivalence between such curves. So to conclude, the main finding of our work is that artificial kagome spin ice's initial magnetization curves preserve a significant amount of information on the phase of its initial microstate, and that this can be used to predict with good reliability the phase of such systems. In turn, this opens the path to the experimental determination of the phases of artificial spin ices using magnetometry techniques, if not alone, perhaps as an additional tool to imaging techniques. So instead of directly putting your sample on a microscope, you can do a preliminary characterization with it. And there's plenty of other interesting perspectives to follow. For example, explore in more detail the physical meaning of those parameters, include in our analysis microstates closer to the phase transitions and see how the performance changes. Evaluate the impact of imperfections, for example, roughness on the nanomagnets on the recognition process, and also try unsupervised classifiers to study new systems for which the phase diagram is unknown. So yeah, I would like to acknowledge the the funding agencies for the financial support. For those who are interested, I invite you to read our full article, and thank you for your attention.
Right. Right. Thank you, Mr. Bruno. So if you have any questions, please raise your hand. Unmute. Or you can also write in the chat box. All right. So, we have one question. I'll read that. Could you please clarify what did you use as parameters? I'm sorry, it's not. What did you use as parameters for your classification?
Yes, so these were the parameters. So I mentioned just as an example the initial magnetic susceptibility, which is the slope of this initial part of the curve. But each of these parameters have like very specific definitions. So let's put another example. This first boundary field is the field that separates the curve into its initial linear trend to this other region where the curves present more features. The growth length is the length of the curve during this middle region. There is the second boundary field where it separates this middle region to the region where the curve is approaching to saturation. And I mean, I could explain better each of the 6 parameters, but it was really a matter of trial and error to find what parameters would be useful to work as fingerprints of these curves. So perhaps you can like take the details of each one in the article. Otherwise, I would be like too long here explaining each one of them. But it's pretty straightforward to understand and calculate that.
Right. Thank you for answering. I don't see any other question. So thank you, Bruno. Thank you very much for your talk.